Now we're going to do the calculation of a weak acid or weak base, the pH calculation, when in the presence of a common ion or something that brings in its conjugate base or conjugate acid, depending on if it's a weak acid or weak base. It's virtually the same as what we've done, but now we have something on the other side, an actual concentration. Okay, so let's do calculation here. We're going to know the pH of a 0.15 molar HF solution in 0.05 molar sodium fluoride. Let's think for a minute about what's going on here. We've got a solution in a beaker. Put HF in there. We're going to get some H+, we're going to get some F-. We're also going to have some HF because it's a weak acid. So we're going to have all three components. When we put NaF in there, we're adding some more F- and we're adding some Na+. Well, we know the sodium here is the spectator ion or the neutral ion of a strong base. It's not going to influence the pH. It's an ion, it's present, but it's basically a spectator ion. So we've got this mixture here of H+, F-, and HF. We're going to have some real value of F- because of the sodium fluoride. So when I write my equilibrium expression, HF plus H2O goes to hydronium plus fluoride. I know the Ka for this, I know the Ka for HF, and here's my association. I have 0.15 molar, but notice, sodium fluoride, I'm going to get 1 mole of fluoride per sodium fluoride, so if I have 0.050 molar sodium fluoride, I have 0.050 molar F-. That's going to be the difference. We call it the common ion effect. We're adding an ion. It's going to change the normal equilibrium. Le Chatelier's principle tells us this is going to shift back to the left relative to the normal equilibrium that HF would produce. Well, if it shifts back to the left, it's raising the pH. It's pushing the pH towards base, or towards neutral, really. Okay, so but what's going to happen here? We're still going to lose some of this. We're going to gain some hydronium, and we're going to gain some fluoride. So at equilibrium, we're going to have 0.15 minus X, and 0.05 plus X. Now let's build our equilibrium expression. It's going to be no different than what we've been working with. It's going to be these two ions, hydronium and fluoride, divided by the concentration of HF. Well, that's X, but this is not X now. Fluoride is 0.05 plus X. So I'm going to plug that in, times 0.050 plus X. Then I'm going to divide by the HF concentration, which is 0.15 minus X. 0.15 minus X. Now, to prevent having to use a quadratic formula, I'm going to say the minus X here is negligible, the plus X here is negligible. They're both going to drop. Anything's plus and minus can be dropped off. We're going to check it, doing the 5% at the end. 7.2 times 10 to the minus 4. So, X, we're going to multiply over by 0.15 and divide by 0.05. So we're going to have X equals, no square root here because I don't have X squared. So very important you notice that. It's only X. X equals 7.2 times 10 to the minus 4 times 0.15 divided by 0.05. Plug that in the calculator here, and we're going to get 2.2 times 10 to the minus 3. Well, we need to do a check on that. When you do that check, do the check relative to the smaller of the two concentrations. Meaning if it's less than 5% relative to 0.05, then it's definitely less than 5% relative to the larger 0.15. So I go over here and do my 5%. Say, okay, I've got 2.2 times 10 to the minus 3 divided by 0.05 times 100. Plug that in, I'm going to get 4.3%. We're good. We definitely have the right, or less than 5%. So what does that mean now? Well, this is hydronium. It's not fluoride, but it is hydronium. So this is the hydronium concentration. If I wanted the fluoride concentration, the fluoride is 0.050 plus this, which would be 0.052. So now we have a fluoride concentration that's not equal to X. Important for us to see that. We could also get the HF concentration, which is going to be equal to 0.15 to two significant figures, so we can get a change here. Okay, so I have a hydronium concentration. I'm going to calculate a pH. Negative log of 2.2 times 10 to the minus 3 is going to give me a pH of 2.67. And we have the the pH of a solution which has a common ion present, 0.05 molar NaOH. Let's do one more of these. What is the pH of a 0.15 molar methylamine solution in 0.25 molar methylammonium chloride? We have the Kb of methylamine. I've got to be able to look at this and see that it's a salt. I break at the chloride, recognize that chloride comes from a strong acid, therefore it is a neutral ion. So I have a conjugate acid-base pair here. Let's write out our dissociation in water. In water, methylamine will act as a base because it has an active lone pair. When it does, H plus is going there. It's going to receive an H plus and leave behind hydroxide. Well, let's do our ice expression. We have 0.15 of the methylamine, 0 hydroxide, but we do not have 0 methylammonium. We have 0.25. Since there's 1 methylammonium here, 0.25 will be our concentration. Then we're going to say minus X plus X plus X. We know the Kb of methylamine, so let's set up the Kb expression. Kb is equal to methylammonium ion, go ahead and write these out, times hydroxide divided by methylamine. We're going to have 0.25 plus X. That's methylammonium ion concentration. Not X, it's 0.25 plus X. Times X for the hydroxide concentration divided by 0.15 minus X. All that equals the Kb, which is 4.4 times 10 to the minus 4. So okay, we're going to assume this is negligible. We'll also assume that is negligible. We'll multiply those over, and X is going to be equal to 4.4 times 10 to the minus 4 times 0.15. So in the denominator, so you can go with the numerator there, divided by 0.25. Notice, it's not a square root there. This isn't X squared. These X's are gone. This is just X. Well, we do that calculation. X equals 2.6 times 10 to the minus 4. We do our 5% check. As long as we're less than 5% of the smaller of the two values, which would be 0.15, we're good. 2.6 times 10 to the minus 4 divided by 0.15 times 100 will give us 0.18%. We're good. That check tells us we're good in what we assumed. Now we can look at what is X. Well, X is the hydroxide concentration. It's not the methylammonium concentration. This is 0.25 plus X, which is basically going to be 0.25. C2H5NH3 plus equals 0.25. This is too small to change 0.25. So it equals 0.25. Well, if I have a hydroxide, I can calculate the pOH of the solution. So I'm going to take negative log of 2.6 times 10 to the minus 4. I will get 3.59. So my pH equals 10.41. Basic pH is what I expect here. Even though I have the presence of the methyl ammonium, the conjugate acid. I have the conjugate acid at a concentration greater than the base, it's still a basic solution in this case. So this is how we're going to calculate the pH of a solution where its salt is also present, or its conjugate acid, conjugate base is present.